quickly introduce myself. My name is Timo Schmidt, and I'm at the University of Augsburg in Germany in the group of Manfred Albrecht, looking for spin textures in magnetic materials. Normally, Manfred Albrecht would give this talk to you, but he unfortunately couldn't come, so I'm taking his place, and I'm glad being here. And the topic today will be dipolar-stabilized first and second order antiskyrmions in ferrimagnetic materials, or multilayers. So let's get on with the motivation. Like, the motivation for everything skyrmion based is basically since 2008 or 2009, the racetrack memory. And you could imagine that if you had a material where you could stabilize skyrmions, you could build a racetrack memory where you can say if a skyrmion gets by the detection, then it means a 0. And if no skyrmion gets by the detector, that means a 1, or the other way around. Doesn't matter really much. But the problem with that approach is that that the distance between the skyrmions, which would act as a 0 or a 1, is very volatile to pinning and other thermal fluctuations. So it would be a better approach to use different spin textures, like, for example, in this animation, an antiskyrmion as a 0, to get this distance between the individual particles right. But for that, you would need a material that can host both skyrmions and antiskyrmions under the same conditions. Another thing that is like holding racetrack memories back is obviously the Hall effect, which deviates the skyrmion when it's driven with a current that is spin polarized in one direction. So it could annihilate at the edge, and we don't want it. But we can also use that skyrmion Hall effect to our advantage, for example, in these skyrmionic interconnections, where you could say that these particles with no topological charge, so no skyrmion Hall effect, could travel straight through, and these other spin textures with a negative or positive spin Hall effect, spin Hall angle, would move to the sides. And that would have the advantage that you didn't need one connection for these textures and one connection for these, but you can have a shared connection, which would, like, you would need less connections and less material, obviously. And the last point is coming up like recently. Skyrmions can be used for unconventional computing, to be more precise, for neuromorphic computing, where you try to mimic the function of a human brain. And there has been applications proposed that can act as neurons and ones that act as synapses, both with skyrmions. And you could also, with that approach to computing, could potentially solve a really important issue in computing right now, namely the von Neumann bottleneck, which is the problem that at the current von Neumann architecture, you have a processing unit and you have a memory unit, but they are apart from each other. So there is a time limit at how fast you can exchange information between these two. But with skyrmions, where you can have these processing units and also skyrmions for memory units, that could possibly be overcome. So let's get on with some previous work on skyrmions and basically antiskyrmions. There has been a lot of research on skyrmions. Obviously, the research kind of exploded after they were found, but not so much on antiskyrmions. Antiskyrmions have been stabilized in these Heusler compounds with their symmetry of D2D. You can see here some atom pictures of these spin entities, which are really well aligned in that lattice. And another, oh, that was the wrong key. And another example could be in Schreiber side with S4 symmetry. And in these materials, the skyrmions are stabilized by the Dzialushinsky-Morier interaction mainly, the DMI, and also through its really, and through its symmetry reasons. But we took kind of another approach with our antiskyrmions. So this is basically what our system looks like. It's a ferrimagnetic multilayer consisting of iron and gadolinium at very low thicknesses for each layer. And if you imagine that if you sputter such a system, then you can say that it's more of an amorphous alloy than really a multilayer. So that every iron has enough gadolinium partners nearby to get this ferrimagnetic interaction. And it's also gadolinium dominant. We orientated ourselves for that at the works of Montoya et al., which you can see here, and this group worked on this iron gadolinium 80 multilayers and tried to stabilize Bloch skyrmions by the dipolar interaction. So no DMI interaction, but dipolar stabilized skyrmions. And I made this phase map, which shows the saturation magnetization and the uniaxial anisotropy. And there are a few regions here. So in the first region, where it says Q is greater than 1, Q is our quality factor, which is defined by the uniaxial anisotropy divided by the shape anisotropy. And because the shape anisotropy scales with the saturation magnetization, this is like a parabola kind function. And for these values, we don't get skyrmions. So we want to have a greater shape anisotropy than uniaxial anisotropy in these films. And also for that region, they found that they had in the green, they had a skyrmion lattice, and for the blue dots, they had isolated skyrmions. So also the value of m squared over k to the power of 3/2 is important in that case. And we recreated that basically to get ourselves dipolar stabilized Bloch skyrmions, which have a rotational sense. And now the approach was, what happens if we stuck iridium layers inside the top and the bottom? Like we made a few samples with different numbers of iridium layers, because iridium has a really strong spin-orbit coupling, and it basically introduces DMI to the system. So we have a Bloch type characteristic from our iron and gadolinium, and we could have this Neal skyrmion characteristic type, because in the DMI systems, most skyrmions form for a Neal type. And then the question was, if we get this Bloch rotational sense combined with a Neal skyrmion, can we get this antiskyrmion spin structure, which is basically just Bloch domain walls separated by Neal domain walls. And I wouldn't be standing here if it didn't work. So I'm going to show you the results we got. One point, all of our samples were sputtered on silicon substrates and also on membranes. So we had the ability to transmit an electron beam through it and do Lorentz microscopy on that. So on that picture, we got a lot of things. So let's start with this one. That is a white dot with a black circumference, and it represents a counterclockwise Bloch skyrmion. Oh, that was already, yeah. So at the top, you always see the picture of the real thing. And on the bottom, here is the spin structure we would expect from such a spin object. And in the middle is a simulated Lorentz contrast, which is basically just a really easy Python program that calculates how an electron beam, if it would propagate into that texture, would be deflected. And in that case, this Bloch skyrmion would act as a focus lens. So the electron beam would get focused in the middle and leave a black circumference around it. So that is a Bloch skyrmion, these white dots. And there are also black dots, which is a clockwise Bloch skyrmion. So it's the same principle, but this time it acts as a defocus lens. So we get a black dot and a white circumference in the middle, and also that matches really good with our simulation or our experiment. The next thing we have here is a bubble, a type 2 bubble, we call that. And that differentiates itself a little bit from the other objects. So this is an object that is not topologically protected in that sense. So you could have a uniform transformation to get that into the saturated state. So it's not topologically protected and not that stable. But also here, the simulated picture really fits the measured one really well. Now we get to the interesting part. Here we first have our first order antiskyrmion, let's call it that. And we saw that contrast earlier. We have here these 4 Bloch type walls, up, down, bottom, and right, divided by these Neal type walls. And you can imagine that in this direction, it acts as the focus length from here. So you get 2 bright spots, and from up and down, it acts as this kind of rotation. So we get these dark spots. So like a cross from a white and a dark spot. And we wouldn't call it first order antiskyrmion if we hadn't had a second order. And we are really proud of that, because that is, to our knowledge, the first time that thing was experimentally measured. And it basically behaves as a first order antiskyrmion, but it has one more iteration of a Bloch and a Neal type domain wall. So you get this radioactive sign if you want. So yeah, that are the different spin textures we could stabilize at also the same conditions, like at 260 K for 2 iridium layers inserted in that. Now let's see how our hysteresis loop is connected to the spin structure formation. The first thing we see here in the hysteresis loop is that the in-plane loop saturates faster than the out-of-plane loop, which is expected, as we said, that our shape anisotropy, which lies for a thin film in plane, should be greater than our uniaxial anisotropy. And so this is that. And another thing you often see at Skyrmion samples is the small opening at the out-of-plane hysteresis loop, which comes from that the nucleation and the annihilation of Skyrmions is an irreversible magnetization process. So if you go from zero field up to the saturation, you get another way, let's say it, than if you go down. So let's go that way. At zero magnetic field, we have here really tight labyrinth domains. If we go further up, okay, thanks. So if you increase the magnetic field, then you see that the periodicity of the stripes gets smaller, and you can also make a distinction between these big black and big white domains and the gray domains. And the white and the black domains are basically the ones with chirality, and the gray ones don't have chirality. And you can also in the picture see first Skyrmions forming. If you increase it further, we can see now that the trend continues. Basically, we have some Skyrmions, and that was it. So then we increase it further, and now all of the domains of the stripe domains have been broken apart into a lot of bubbles, a lot of Skyrmions, and also some antiskyrmions here, here, and here. And because we know that our bubbles are not topologically protected, they're also not that stable in front of a magnetic field. So another increase lets them vanish almost completely, or completely, I guess, in that sense. And only the antiskyrmions and skyrmions remain. And the next step, if you increase it one step further, is that also the antiskyrmions annihilate, because they are not as stable as skyrmions. So we can translate that into some stability ranges our bubbles have the lowest stability in this range, around 100 milliteslas of magnetic field. Our skyrmions have a wider range, are quite stable, and our antiskyrmions are a little bit more, so they go until there, are a little more stable than our bubbles, but not as stable as the skyrmions at all. And this trend also continues, so our antiskyrmions of second order are less stable than our antiskyrmions of first order. And I also brought you a little film to see it with your own eyes. So we increase the magnetic field, and you see that the domains get bigger, and there are some skyrmions here, 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 and now everything breaks up into bubbles. The bubbles disappear. There were antiskyrmions for a second, but I couldn't talk fast enough. And after that, we're in this iteration, and everything annihilates. The picture is a little bit shifting. That is because if you excite the system with a magnetic field in the Lorentz stem, the beam also gets a little bit shifted. Yes, but that for the experiment, and our friends from Vienna, thank you, Sabri, also did some micromagnetic simulations for us with these parameters. And I also have a film for that. So we have a little bit more zoomed in picture of our structure. And we can see these walls getting smaller. And I guess here are round particles forming. And you then can see that like all of the striped domains break up into bubbles eventually, like somewhere around here. And then the bubbles disappear because they're not really stable. Then the antiskyrmions, you can't really tell the antiskyrmions, I guess, from that perspective, but the skyrmions are the most stable, and they stay there until it's so. Yeah, a good fit to our experiment, let's say that. So let's talk a little bit about the nucleation of antiskyrmions, because we noticed like a trend for these nucleation sites and why they nucleate. And the trend is that they often nucleate at sites where 2 or 3 domain walls meet each other. And you can see such an incidence here. And this is one domain wall, this is one domain wall, this is one domain wall, and this is basically a Bloch point. We're at 76 millitesla for that. And if we increase the magnetic field, you can see that this domain wall detaches from there and leaves this there. And another increase in magnetic field shows that another domain wall will lose its grip on that structure. And you can almost see a full antiskyrmion here. And with another increase, we are basically there. And we've seen it a lot of times in at different spots where these 3 domain walls meet and an antiskyrmion comes out of that. But we have to experiment a little bit more to qualify that really. But also we have simulations for that, which also show a very similar picture for this formation of an antiskyrmion. Good. So now we have a little bit of an antiskyrmion recipe, let's call it. So Montoya et al. Did their phase map, and we thought let's do one ourselves. So we have here this region where Q is greater than 1 or Ku is greater than K shape. So that is basically forbidden area, and we can then just transfer that data from Montoya et al. So these are only skyrmions, so no antiskyrmions in their films. And if we add our own, so then we have here like these coexisting antiskyrmions and skyrmions in violet, and the skyrmions, like samples which only had skyrmions, in the blue squares, and also in plane domains, like basically here where the Ku value is just too low to get these out of plane things. And with a little bit of simulation data for these stable antiskyrmions and stable skyrmions, also from our friends from Vienna, we see that this phase map also agrees very well with the experiments. And yeah, so that is basically the recipe to get antiskyrmions. You have to somehow get in that phase pocket. But the question is, okay, we can make our samples so that they have this this value of uniaxial anisotropy and saturation magnetization. But is there a way, for example, if we make a sample and we see, okay, it is up here, like 40 kilojoules per cubic meter and 200 kiloamperes per meter. So we would be out of that pocket. Is there a way to do that after deposition, to somehow shift that like down or to the side to get into that phase pocket? And the answer is yes, we try to do that with local post-deposition anisotropy engineering. And the idea with that is that we irradiate our films with helium ions. And you can see from that MFM pictures that before irradiation, you have your labyrinth domains you would expect from your films. And with a higher dosage of these of the helium irradiation, you get a little bit more fuzzy here. And at 10 to the power of 15 ions per square centimeter, you are just so in plane from your irradiation that there are no more skyrmions or stripe domains forming. So basically also for this labyrinth domains, you need a little bit of competition between those in plane and out of plane moments, and you destroy that with ongoing irradiation. So that is really an in-plane film. And the next thing was the local part. So what we did was we took our iron gadolinium multilayers with the iridium, and we tried it with nanospheres. So these nanospheres, we have had different sizes of these, and they were between 200 and 800 nanometers. And we put that in an aqueous suspension and then evaporated this aqueous suspension so that the nanospheres could align on that multilayer really neatly. And we got a picture of a SEM here, which shows that they really form a really good hexagonal lattice. And the next step would be to irradiate it with helium ions. And you can guess that the helium irradiation can't transfer through the nanospheres, so it only gets in between the nanospheres, and you only destroy it like that, your area where you don't have your nanospheres. And then if your nanospheres are approximately the size of your skyrmions, then you basically have a hole where these skyrmions can form in. And out of that hole, there are like forbidden regions for them. And so we can remove the nanospheres and then look at it with the MFM. And we really see some round objects here, almost in a hexagonal lattice. It gets a little bit confusing around here, but there are areas where you can really see that hexagonal lattice from the nanospheres. Looks like it's working really good, but there are some problems with this technique. At first, from that picture, we have no insight like on what spin object that is. So this could, like the MFM is only sensible to the out of plane magnetization. So this could be skyrmions, this could be antiskyrmions, this could be bubbles possibly. So we don't know. The better approach would be to make this kind of experiment on a membrane and look at it through Lorentz temp. But the removing of the spheres in precisely damages the surface. So this is a picture of a sample that has its nanospheres removed, and that is not an MFM picture. This is a height picture. And so you can see where this nanospheres was and were. And there's approximately like 3 nanometers of film they just rip off when they get removed, because they like glue a little bit to the sample. And with membranes, for membranes, it's not suitable because you would damage your membrane and you wouldn't see anything. So the question is, can we realize it another way? And now comes the outlook. We could do that on membranes with focused ion beam ionization. We have made some experiments with that, but one are not really far. But the idea is basically, if we irradiate parts of the sample where the skyrmions shouldn't be, and we leave parts unharmed where they should be, then basically the skyrmions should only be allowed to enter that part or be in that part of the sample. We could do some things like these artificial racetracks, where you don't need like nano strings, but could use it that way. Or what you can also do with that is something like that, where you have these hexagonal irradiated regions, which leaves these crossings where the skyrmions can meet, or the stripe domains can meet. And as we have seen, like that antiskyrmions are more common to nucleate from these crossing points of the main walls, we could use such a structure to get more in detail about the nucleation of antiskyrmions. And another outlook thing would also be, we have found now antiskyrmions of our first order, and we have found antiskyrmions of the second order. So what about higher orders? Like, these are simulated pictures, but could something like a third order antiskyrmion or a fourth order antiskyrmion exist? Yeah. And that's basically it. So I hope I could pique your interest a little bit in the research we do in the University of Augsburg. And now I would be open for questions. So thank you very much.
Thank you. Questions or comments? Yes, please.
Very nice work. I really enjoyed it. Thank you. One question, maybe I missed your explanation. What's the mechanism for stabilizing such antiskyrmion? I saw usually you need some asymmetric DMI.
Yes, but in this case, we are dipolar stabilized. So
Yeah.
we also measured the DMI strength. Wait. There are a lot of animations. So yeah, I skipped the part also a little bit. We also measured the DMI constant, and it's basically pretty low. Apparently, the insertion of the iridium layers did provide us with some DMI, but not as many as as much as we like thought it would. And another thing this insertion of iridium layer did was basically it reduced the saturation magnetization. So for some point, we also went from somewhere we are here, like to there. But our antiskyrmions and skyrmions are dipolar stabilized, basically.
So it doesn't invoke any asymmetric DMI in this case.
Well, I guess not.
Okay.
For the stabilization. Not.
Also, I remember Eric Fullerton was telling me in that system they saw 3D structure. So like in the middle, there's a Bloch skyrmion, and then there's neo cap on top and bottom. Do you see any depth-dependent variations of the spin texture?
Could you explain it a little bit? I guess not.
So their system is without this iridium, it's just the iron gadolinium, and they saw typically you see the Bloch skyrmion, but there's no cap. So the top and the bottom, there's a different configuration. I wonder whether you see any depth-dependent variation in your field.
Well, I guess we have only measured like Lorentz stem, and you are not like height sensitive with Lorentz stem. So I don't know, actually.
Okay, thank you.
Yes, please.
Thank you. So you're saying that the skyrmions and antiskyrmions are stabilized by dipolar interaction. So I don't really understand what is the role of iridium, because you're saying that it introduces DMI, but in the end, they're not DMI due to DMI.
In the end, it's it introduces DMI, but wait, just the wrong direction. Sorry. We thought that it would introduce more DMI, but it effectively said reduces the saturation magnetization, which was also like a point from getting like somewhere here, where Montoya et al. Were to getting into that phase pocket.
But why does it reduce the magnetization? The magnetization, I don't understand, because the iridium. Yes.
We are also not that sure. It could be that I read that the iron and the iridium could like couple, or they. Yeah, I'm really not that sure about that.
I don't think
but
there is a strong induced moment on the iridium.
It definitely reduces the saturation magnetization, because we had like films with without them and with some iridium layers, and the saturation magnetization goes down. What the reason for this is, I'm not that sure, but yeah, basically we don't have DMI as we expected it. I hope that's somehow answered.
Yes.
Okay, thank you. Maybe related to the same question. Are you sure that you can change the saturation magnetization without changing the DMI, and that you get antiskyrmions without DMI? Like it seems to be there.
I guess we have such low DMI that it can't be a stabilizing factor, and that the dipolar interaction in our films is the main factor for this stabilization, yes.
Okay, and then DMI and saturation magnetization here are two independent parameters, or anytime you move one, you move the other?
I guess they're fairly independent.
Okay, thank you.
Yes.
Thank you for your